pre-calculus students. Welcome to section 4.1b. Still radian and degree measure. We have to finish our notes because there's a lot of them. Almost all of this, I think all of this you learned in Algebra 2, right? But we need a refresher before we go on to information that you haven't learned in Algebra 2. So bad news, there's going to be a 4.1c video because I ran out of board. I thought there'd just be an A and a B, but there'll be one more video that has just 2 examples on it, so we can fit it on. Okay, so let's continue. Number 4. From video A. Now we're moving to coterminal angles. Coterminal angles have different measures, but if you were to draw them, they would make the same picture. They would have the same terminal side if you started their initial sides on the horizontal x-axis, okay? And that's simply because we can rotate more than once. Right? We can rotate 360 degrees in a positive direction or a negative, and we can rotate a radian measure, right? 2 pi in a positive direction or a negative. So let's take a look. So to write coterminal angles to an angle you've been given in degrees, just add or subtract 360 as many times as you want. There's an infinite number of coterminal angles for each angle. If it is in radians, then you simply add or subtract 2 pi. You might need a common denominator, and that's okay, right? We know how to do that. So let's write angles that are coterminal to. So let's first add in write an angle that is coterminal to 60 degrees by adding 360 to the 60, and we get 420 degrees. So if you rotated 60 degrees, your angle would be right here, correct? If you rotated a positive 420, you would start on the positive x-axis, rotate 360, and you'd say, oh, I have to go 60 more, and you would have the same terminal side. Another thing we could do for 60 degrees for a coterminal angle with a different measure is subtract 360, right? So if we take 60 and we subtract 360, we get a negative 300 degrees. Obviously a different angle measure than 60, right? Again, here is our 60-degree angle. If I had you rotate a negative 300 degrees, you would go negative 90, negative 180, negative 270, and say, oh, I have to go 30 more. There's a negative 300, and you would have the same terminal side. Let's work with radians. So 60 degrees is pi over 3 radians, right? Okay, easy to see because pi is equal to 180. And 180 divided by 3 is 60, super easy. So we're going to take pi over 3 and we're going to add 2 pi to it. The problem is this is 2 pi over 1 and I can't add it to pi over 3. So I'm going to write my 2 pi as 6 pi over 3. Right? Isn't that still 2 pi? Right? And we'll add it to pi over 3. And we get 9, oh, not 9, bad math, 7 pi over 3. There we go. If I rotated pi over 3, or I rotated 7 pi over 3, I would have the same terminal side. Let's subtract 2 pi. This means we have to subtract 6 pi over 3. So pi over 3 minus 6 pi over 3 is a negative 5 pi over 3. Rotating in radians might be a little harder for you, but let's give it a try. Right, pi over 3 is 60 degrees. So here's pi over 3 right here. Okay, I'm going to rotate pi over 3, that's 60 degrees, a negative 5 times. I'm going to count Ready? So here's 1 pi over 3, 2 pi over 3, 3 pi over 3. Notice that's pi, and I'm in the right spot, right? 4 pi over 3, 5 pi over 3. Look at that. When I rotated a negative 5 pi over 3, I landed in the same place. That takes a little practice. Another reason why radians are important is formulas. For these formulas, arc length, area of a sector, angular speed, and linear speed, all of our formulas, the theta, right? That's what we use for an angle measure. It's called theta. Remind me to tell you about the Math Cafe I want to open sometime. And I want my onion rings to be theta rings. Anyway, we'll talk about that. So all the theta, all the angle measures must be in radians. That's what makes these formulas so easy. So arc length, they use an S for arc length, which I think is kind of cool because there's 2 arcs in an S, right? And the arc length equals the radius times theta. Now that seems pretty easy, okay? Let's look down here. Why is that true? So an arc length is just a part of a circumference. And it's really because if I asked you, well, what is the formula for a circumference? You would tell me all the way around that it's 2 pi r, right? 2 pi r all the way around. Let's see, right? And then I say, well, I have some theta out of 2 pi though. I have some fraction. I have this theta out of the total 2 pi. And take a look at that. The 2 pi's cancel and I get r times theta. That's where the arc length formula comes from. The area of a sector is 1/2 r squared theta. That's like a piece of pie, right? It's an area. And the reason is if you wrote the formula yourself, right, you would say, well, okay, I don't know the formula for that piece of pie, but I do know the formula for the whole area. That's pi r squared, right? And then I go, I'm going to have to multiply it by, I have a fraction though. I have theta. I only have a part of the area. I have theta out of 2 pi. And take a look at that. The pi's cancel. And I have a 1/2 r squared theta. So that's where the formula comes from. Then we have angular speed. Angular speed, they call W, and that is theta times divided by time. How many angles, how many radians do you turn over time? So notice it's important because like if you had people on a carousel, right, in different places, some people on the inside, some people in the middle, some people on the outside, they all have the same angular speed. They all make one rotation of 2 pi in the same amount of time, okay? And so they call that W, theta divided by T. Linear speed is different though. Notice that the people on the carousel who are in the inside, their path is shorter than the people on the outside, right? So if you straightened out that curve, the people on the outside of the carousel would have a higher linear speed than the people on the inside, right? Because you're going further in the same amount of time. So V is the linear speed, and that is simply the radius times the angular speed, right? Because if they're all going the same angular speed, what matters is what radius are they on, right? On the inside, they have a smaller radius. On the outside, they have a bigger radius. So notice that you can put this in a couple different ways then. This is linear speed, but notice that r times theta is s, right? So you can do it as s over t, or notice that angular speed is theta over t, and so you could call it r times w. So there's like 3 ways to do linear speed. Okay, we're going to do degrees, minutes, and seconds, okay, on our calculator too. And it might be a little hard to see. So we're going to do the best we can here, but in the classroom, we may have to do more with this under the projector. So we not only do we measure angles in decimals, right, but we also do it in what's called degrees, minutes, and seconds. And in fact, let me see if I have it on my phone here. But if you notice, if you pull up your phone, let's see if I'm not sure where I put it. Oh, here it is. Is that it? No, it's not. I should have looked ahead of time. Here it is. I have a compass, right? I have a compass on my phone. Do you have a compass on your phone? And this is kind of cool. So you can see where I am. I live in Clinton Township, right? And it says, look at that. It says at the bottom where my latitude and longitude, and that is in degrees, minutes, and seconds. Notice right where it says 92 degrees east, right below that, above Clinton Township, right? It says those are degrees, minutes, and seconds. Isn't that cool? It's right on your phone, you know, your location. So, so we like to say, you know, where we're located in angle measure in degrees, minutes, and seconds also. And we have that on the calculator. So DMS, we call that degrees, you know, the degree symbol. Minutes are actually a quote, a single quotation mark. And that minute is 1/60th of a degree. And then a second is a double quotation mark, and that's 1/60th of a minute. So just think of that. Imagine a circle, 360 degrees, right? So each one of those degrees is very, very small. A minute is 1/60th of each of a degree. And a second is 1/60th of one of those minutes. So very, very small. So how do we do this on the GC, on the graphing calculator? It's under second in apps. So if you look on your calculator, right, where's the apps button? Right here, it's in purple. And if you look above it, it says angle. So if you do second apps, notice number 1 is degree, number 2 is minutes. Where are the second, and number 4 is where you switch to degrees, minutes, and seconds. Where is the quote, this double quotes for seconds? It really kind of bothers me. They must use it for something else, but it's not on second apps. It is, I have it on the board, alpha plus. So when you look above the plus sign, right, if you use alpha plus, so alpha and then plus here, there's the double quote marks. So let's take a look. Let's say that we have 226.125 degrees, right? So this is an angle measure in a decimal form, and we want to change it to degrees, minutes, and seconds. All you do is put 226.125. You can put the degree symbol on it if you want, but you don't need to. So I just put this into my calculator. Right, here we go. Right, then I hit second apps for angle. Here we go. I go down to number 4, degrees, minutes, and seconds. There we go. And you hit it. And there you go. It gives it all to you. 226 degrees and 7 minutes and 30 seconds. We used to have to do a lot of math with fractions to switch from decimals to degrees, minutes, and seconds, but we don't need to do that anymore. How about going back the other way? 15 degrees, 18 minutes, 45 seconds. All we have to do is get the symbols on there and hit the button, and it'll give us a decimal. So first of all, 15, here's my 15. And of course, I'm gonna do angle, second apps, and put the degree number 1 on it. Now I'm at 18 minutes. So 18, there we go. Angle and number 2. And then for 45 seconds, that double quote for the seconds is above the plus button. Here we go. And now all you have to do is hit enter. And it gives you 15.312 in 5. There you go, as a decimal. All right, class, one more video with 2 examples in it. All right, see you in a minute.